what determines a planet's temperature? It's actually a very simple equation, the only equation we'll encounter in this entire set of lectures. Energy in equals energy out. Pretty simple, right? Now, you may not have thought about this before, because you think of the sun as radiating energy to the Earth and the Earth receiving the light and heat and making it a habitable planet. But if that's all that happened, the Earth would be like an oven without a thermostat. Energy flowing in, no energy flowing out. It would get hotter and hotter and hotter. In fact, there is a perfect balance between the amount of energy flowing in from the sun and the amount of energy the Earth radiates back into space. And for the Earth, for the Moon, for Mars, for any planet in any solar system, the temperature is largely set by that simple balance of the amount of energy coming in and the amount of energy going out. Now, there are a number of components that contribute to both sides of this equation, and to understand how they work and whether changes in them can be responsible for the rapid increase in temperature, we need to examine them in turn. And so let's start with the energy in side of the equation. And the first component there is the obvious one, the amount of energy the sun puts out. The sun's output we've measured very precisely. It's 3.839 times 10 to the 26 watts. That's a lot of light bulbs. If you look at all the zeros, they're spelled out there. The question is not what the average energy output of the sun, but does this change with time? And the answer is yes, because of sunspots. If you look at the sun, and don't do that without special equipment, you will see a glowing orb dotted with tiny little black specks. That's if you look with your eyes. These little black specks are called sunspots, and they arise from the eruption through the surface of the star of magnetic storms that are taking place beneath the surface that we can see. They rotate around with a period of 26 days. That's how long it takes the sun to rotate. And they last a month or two before they fade away and new ones pop up somewhere else. Now, to our eyes, the spots look black, which suggests they're radiating less energy. But in fact, in parts of the spectrum that our eyes can't see, in the ultraviolet and the X-ray and the radio, they're actually putting out more energy than the quiet sun. So more sunspots means more energy. How does this change compare to the sun's total output? In this diagram, we see measurements from satellites above the Earth's atmosphere, and one must get above the atmosphere to do such measurements, of the mean solar output. And we can see that it starts at some level and then gradually over a few years falls to a lower level with fewer fluctuations and then rises again with more fluctuations and then falls with fewer fluctuations. That's what's called the sunspot cycle. It's 11 years. Why it's 11 years, we don't have a clue. But it is every 11 years we reach a peak of solar activity and then a valley a few years later. And the total peak-to-peak amplitude is about 0.1%, 1 part in 1,000. Not very big, but measurable and potentially important. The diagram shows that we've kept track of this over the last 400 years or so, since Galileo first discovered sunspots with his first telescope in 1610. And you can see this 11-year period up and down and up and down and up and down. You can also see that it varies. Some minima get very close to 0 sunspots. Some maxima, there are as many as 250 sunspots on average on the sun, whereas in others, there's fewer than half that number. And we know that, for example, in the 17th century, that there was a period when very few sunspots were observed, and that was the coldest period in the last 2,000 years, in Northern Europe at least. So again, more sunspots means more energy coming from the sun, which naively would mean the Earth gets warmer, fewer sunspots, less energy coming from the sun, and the Earth might get cooler. If we look just over the last 70 years or so, we can see there are 6 of those 11-year cycles, and we see that the recent one, the one from 2010 to 2020, is by far the lowest. Indeed, it's been the lowest in more than a century. Fewer sunspots, even at the maximum, and no spots at all at the minimum. You would expect, therefore, since more spots means more energy, that the Earth would have been cooler during this period, whereas in fact, we've had 7 out of the 7 hottest years in the last 150 years. Recently, the sun was very, very quiet in 2020, more than 50% of the days had no sunspots at all. And yet, these are the warmest years we've ever experienced. So if one considers solar output as the only important variable here, we would have predicted a lower Earth temperature, and what we've observed is a much higher Earth temperature. Now, in the last year, the sunspot cycle has come out of its minimum and it's ramping up again. And by 2022, it's already a factor of 2 above where it was 11 years ago. So we may be returning to a more active sun, which means more energy, which means an even warmer Earth.